95% of the universe is made of stuff we cannot see. Everything you have ever touched, every star in the night sky, is just a tiny fraction of reality. The rest is a profound cosmic mystery, a hidden realm of dark matter and dark energy that dictates the fate of everything. This is the grandest detective story ever told, a race to decode the universe's most enigmatic energies. By the end of this journey, you will understand how this search is rewriting our most fundamental ideas of space, time, and existence. We will journey from the invisible scaffolding that holds galaxies together to the repulsive force tearing the cosmos apart. What if the world we see is merely the tip of a vast, dark iceberg? What force is causing the universe to expand at an ever-increasing rate? This exploration begins by pulling back the veil on the very fabric of space itself. How does it feel to know that most of reality is completely invisible to you? Think of the universe as a vast cosmic ledger. On one side, we have a meticulous accounting of everything we can see and touch. The brilliant stars, swirling galaxies, and our own beautiful planet are all entered into this column. For centuries, we believed this was the entire sum of existence. Yet when we finally calculated the total, a shocking truth emerged. All of this, every single atom of so-called ordinary matter, accounts for less than 5% of the cosmos. We are not the main event. We are a rare and precious exception in a sea of invisible forces. This profound shift in understanding began with a few stubborn clues. In the 1930s, an astronomer named Fritz Zwicky was studying the Coma cluster, a gigantic collection of galaxies. He noticed these galaxies were moving so fast that the gravity from their visible stars should not have been enough to hold the cluster together. It should have flown apart. Zwicky proposed the existence of dunkle materie, or dark matter, an unseen substance providing the missing gravitational glue. Decades later, Vera Rubin provided the definitive evidence. She meticulously mapped the speeds of stars rotating around the centers of spiral galaxies. According to the laws of physics, stars on the outer edges should move much more slowly than those near the center, just as Pluto orbits our Sun more sluggishly than Mercury. But Rubin found something astonishing. The stars, whether close in or far out, all orbited at nearly the same incredible speed. The only possible explanation was that each galaxy was embedded within a massive, invisible sphere of matter, a halo exerting a gravitational pull far beyond the light of its stars. This is the heart of the dark matter puzzle. We cannot see it, but we can watch its effects on the things we can see. It acts as a cosmic anchor, its immense gravitational grip preventing galaxies from spinning themselves into oblivion. So our cosmic ledger now has 3 entries. The first is baryonic matter, the protons and neutrons that make up you, me, and every star. This is the 5%. The second is dark matter, the invisible scaffolding that structures the universe, making up about 27%. And the third, the most dominant and mysterious of all, is dark energy, a repulsive force filling the remaining 68% of the cosmos and accelerating its expansion. How does it feel to realize that the world you perceive is the anomaly, that the vast majority of reality is made of substances fundamentally alien to our experience? This humbling realization forces our gaze toward the first great enigma, the silent partner in the cosmic dance, dark matter. Far out in the cosmic deep, astronomers watch as a massive cluster of galaxies acts like a lens, warping the very fabric of space around it. The light from galaxies behind this cluster bends into faint, shimmering arcs, a phenomenon called gravitational lensing. The source of this immense space-bending gravity is a profound puzzle, for the visible stars and gas account for only a tiny fraction of the mass required to create this effect. The true source of this ghostly grip, is dark matter. This is the universe's primary scaffolding, the unseen skeleton upon which galaxies are built and the cosmic web is drawn. Dark matter is fundamentally different from anything we know. It does not emit, absorb, or reflect light. It is completely transparent, a ghost that passes through our world and through itself without a trace. Its only known interaction with our kind of matter is through gravity, the pull we see warping distant starlight. It might also feel the weak nuclear force, the same force responsible for radioactive decay, but this interaction would be so feeble that detecting it requires extraordinary measures. Physicists like Dr. Priyamvada Natarajan are cosmic cartographers of this invisible realm. They use sophisticated computer models and observations of gravitational lensing to map the distribution of dark matter, revealing its intricate, web-like structure throughout the universe. This mapping points to a specific kind of particle as the leading candidate for dark matter's identity, a WIMP, which stands for Weakly Interacting Massive Particle. These hypothetical particles are heavy, yet they barely interact with normal matter, making them incredibly difficult to catch. To find them, scientists have built ultra-sensitive detectors and placed them deep underground, in old mines and beneath mountains. These locations are shielded from the constant rain of cosmic rays that would drown out the faint, telltale signal of a WIMP collision. They wait in profound silence and darkness, hoping to feel the slightest bump from a ghost particle that has traveled across the cosmos. It is crucial to understand that dark matter is not antimatter. When matter and antimatter meet, they annihilate each other in a flash of energy. Dark matter does no such thing. It simply is a vast, passive presence. The most striking evidence for its separate existence comes from cosmic car crashes like the Bullet Cluster. This is a spectacular collision of two galaxy clusters. In this event, the clouds of hot gas, which are the normal baryonic matter, slammed into each other and slowed down. But the dark matter, which does not interact, sailed right through the collision. By mapping the gravity of the cluster, astronomers found that most of the mass was not where the gas was. The dark matter had become separated from the visible matter, proving it is a distinct physical substance, so we are left with a profound and humbling implication. Most of the matter in the universe, the very stuff that sculpts its grandest structures, is a form we have never touched, never seen, and do not understand. The mystery only deepens as we ask the most fundamental question of all. What is this ghostly substance actually made of? This search for the universe's ghost is a grand cosmic treasure hunt, and the prize is a particle that has never been seen. For decades, physicists have pursued two leading theoretical candidates. The first is the WIMP, the weakly interacting massive particle we met earlier. Its appeal lies in what scientists call the WIMP miracle. This is an elegant piece of theoretical mathematics that suggests if such a particle existed with a certain mass and interaction strength, it would naturally have been produced in just the right abundance in the Big Bang to account for all the dark matter we observe today. This idea dovetails beautifully with theories like supersymmetry, which proposes a heavier shadow particle for every known particle in the Standard Model. The WIMP would be a natural outcome, solving two cosmic puzzles at once. The other prominent candidate is the action, a particle that is incredibly light and more like a wave washing through the cosmos. It was originally proposed to solve a different problem in particle physics, but it has the right properties to be a compelling dark matter component. To catch these phantoms, scientists have built extraordinary machines. Deep underground, in places like the abandoned Homestake gold mine in South Dakota, experiments like LUX Zeppelin wait in utter darkness and cold. They are filled with ultra-pure liquid xenon, a vast target for a WIMP to strike. The goal is to detect the tiny flash of light and the minute electric charge from that single, rare collision. The sensitivity required is almost beyond comprehension. One experimentalist described it as listening for a feather to drop during a rock concert, requiring them to block out all other noise from the natural radioactivity of the rocks, the air, and even their own equipment. In space, the Fermi Gamma Ray Space Telescope practices indirect detection, scanning the heavens for the high-energy gamma rays that would be produced if two WIMP ever met and annihilated one another. And at the Large Hadron Collider, physicists try the opposite approach, smashing protons together at unprecedented energies in the hope of creating dark matter particles directly. Other, more exotic candidates are also in the running, like sterile neutrinos, which would be heavier, right-handed cousins to the standard neutrinos we know. The hunt is filled with tantalizing, unresolved clues. For over 20 years, the Dama/Libra experiment in Italy has reported a curious signal. Their detectors see a rhythmic rise and fall in events that matches the Earth's annual journey around the Sun. As our planet moves through the Milky Way's halo of dark matter, the flux of particles we encounter should change with the seasons. This is exactly what Dama/Libra claims to see. Yet no other experiment has been able to confirm this signal, creating one of the most enduring and controversial puzzles in modern physics. It forces a profound question. What does it say about our scientific methods that we build these vast, incredibly sensitive machines, spending decades of our lives, to find something that might not even be there? This relentless, disciplined search for particles pushes at the very limits of our ingenuity, and when the particles remain elusive, it forces us to consider an even more bizarre possibility. What if we have been thinking about this all wrong? What if dark matter is not a particle at all, but a sign that our understanding of gravity itself is broken? But what if we have been searching for a ghost that does not exist? This is the radical question posed by a small but determined group of physicists. They argue that the evidence for dark matter is not proof of an invisible substance, but a glaring sign that our understanding of gravity itself is flawed. For centuries, we have relied on the laws of Newton and Einstein to describe how matter and energy shape the cosmos. What if those laws break down on the immense scales of galaxies? This idea is called modified Newtonian dynamics, or MOND, proposed by physicist Mordechai Milgrom in the 1980s. Its core premise is deceptively simple. It suggests that gravity behaves differently when its pull becomes incredibly weak, like it is in the outer reaches of galaxies. In these regions, the acceleration due to gravity falls below a specific, tiny threshold. According to MOND, when this happens, gravity stops following Newton's familiar inverse square law and becomes stronger. This extra gravitational kick, Milgrom argued, is what makes the outer stars in galaxies orbit so quickly. No dark matter halo is required. The force itself has changed. MOND was remarkably successful at its primary task. It perfectly predicts the rotation curves of many spiral galaxies without any need for invisible matter. It was a simple, elegant solution to the very problem that first revealed the dark matter mystery. To make MOND compatible with Einstein's theory of relativity, later extensions were developed like tensor vector scalar gravity, or TVS. This framework attempts to weave the MOND idea into the very fabric of spacetime, yet for all its elegance on the galactic scale, MOND faces its own profound challenges. It struggles to explain the behavior of gigantic galaxy clusters, where the observed gravitational lensing is so strong that even a modified gravity law seems insufficient without some form of hidden mass. It also has difficulty accounting for the precise patterns seen in the cosmic microwave background, the afterglow of the Big Bang. The distribution of these temperature fluctuations strongly supports a universe built on a foundation of dark matter. The debate creates a fascinating theoretical standoff. On one side, the particle hunters argue that inventing a whole new form of matter is a more conservative step than overturning the universally successful laws of gravity. On the other, MOND proponents see appending the universe with invisible stuff as the more desperate move. This is not the only alternative to the WIMP paradigm. Other ideas linger on the fringe. Perhaps dark matter is made of primordial black holes, tiny black holes forged in the intense heat of the Big Bang itself. Or maybe they are massive compact halo objects like rogue planets or failed stars made of ordinary matter that are simply too dark to see. Yet observations have largely ruled out macho as the dominant solution, and primordial black holes remain a speculative, though fascinating, possibility. So we are left with a fundamental choice between two radically different visions of reality. Do we live in a universe dominated by an unknown, invisible substance that we have yet to detect? Or do we live in a universe where our most cherished theories of gravity, the very framework of our cosmos, are subtly but profoundly wrong? Which requires a greater leap of faith. This theoretical battleground proves that the veil over the cosmos is not just about what is hidden from our telescopes. It is about the very lenses through which we choose to see. And just as we grapple with the nature of the universe's hidden mass, an even more mysterious force was waiting in the shadows, one that would not hide its effect but flaunt it in the most dramatic way possible. Our own Milky Way galaxy is not an island of stars floating in empty space. It is embedded within a colossal, invisible sphere, a halo of dark matter that stretches for hundreds of thousands of light years in every direction. This ghostly architecture is not unique to our home. Every single galaxy we see is built upon this same invisible foundation. Without this dark matter halo, the immense gravitational forces holding a galaxy together would simply be insufficient. The stars would fly off into the void, and the majestic spirals we admire would never have formed in the first place. This relationship between the visible and the invisible was forged in the earliest moments of the cosmos. In the primordial soup of the universe, dark matter held the key. Tiny fluctuations, regions where this mysterious substance was ever so slightly denser, acted as gravitational seeds. These seeds began to pull in the ordinary hydrogen and helium gas through their gravity. As the gas accumulated and collapsed, it ignited the first stars and began assembling the first galaxies. To see this grand process in action, cosmologists run immense computer simulations. Projects like Illustris TNG start with a universe filled only with these slight dark matter overdensities. When they run the simulation forward, applying the known laws of physics, something remarkable happens. The dark matter clumps and draws together, forming a vast cosmic web of filaments and immense voids. The ordinary matter then flows along this invisible scaffolding, pooling at the intersections of the web to form brilliant galaxies. The simulation's final result looks almost exactly like the real universe we observe through our most powerful telescopes. The entire glittering cosmic cityscape emerges from a dark blueprint. The very nature of this dark matter blueprint matters immensely. Cosmologists often describe it by its temperature, which really refers to how fast its particles were moving in the early universe. Cold dark matter moves slowly, and this slowness allows it to clump easily, forming the small-scale structures that eventually grow into galaxies. Warm dark matter is a middle ground, while hot dark matter moves so fast it has trouble forming any small clumps at all. The universe we see, rich with galaxies both large and small, strongly points to cold dark matter as the primary architect. The evidence for these vast halos is written across the sky. We see it in the frantic orbits of small satellite galaxies around our own Milky Way, their speeds dictated by the gravity of the unseen halo. We see it most clearly in detailed maps of gravitational lensing, where the combined gravity of a halo's immense mass warps the light from background galaxies into faint telltale arcs. This invisible framework does not just build galaxies, it connects them, binding the entire cosmos into a single, coherent structure. And as this cosmic architecture settled into place, it set the stage for a force even more dominant and bizarre to take center stage, a force that would not build but ultimately tear apart. The invisible architecture of dark matter had just settled into place when an even deeper mystery tore through the foundations of cosmology. In 1998, two independent teams of astronomers made a discovery so shocking it rewrote the cosmic future. They found that the universe's expansion is not slowing down as everyone had assumed. It is speeding up. This was the moment we met the universe's dominant force, dark energy. To understand the sheer surprise of this, picture throwing a ball straight up into the air. You expect gravity to slow it down, eventually pulling it back to Earth. Now imagine that ball, against all reason, suddenly shooting away from you faster and faster. That is what the universe is doing. The teams, led by Saul Perlmutter and Brian Schmidt, were using distant stellar explosions called Type 1, a supernova, as cosmic mile markers. These supernovae have a known intrinsic brightness, so by measuring how dim they appear from Earth, astronomers can calculate their distance. They can also measure how much the light from these explosions has been stretched or redshifted by the universe's expansion. The shocking result was that the most distant supernovae were significantly fainter than they should have been. The only possible explanation was that the space between us and them had stretched more than anyone predicted. The universe's expansion was accelerating. This discovery earned them the Nobel Prize and unveiled a force that makes up a staggering 68% of the cosmos. Dark energy is the phantom in the engine of the universe, a repulsive gravity that is pushing everything apart. This is its fundamental difference from dark matter. Dark matter pulls, its gravity clumping together to build the cosmic web. Dark energy pushes, its anti-gravity tearing that web apart on the largest scales. The leading candidate for this bizarre force is a concept with a strange history, the cosmological constant. Albert Einstein originally introduced this term into his equations of general relativity to achieve a static, unchanging universe, a notion that was the scientific consensus at the time. When Edwin Hubble later discovered the universe was actually expanding, Einstein called the cosmological constant his greatest blunder. Yet now, it seems he may have been right for the wrong reason. The cosmological constant represents a constant energy density inherent to the very fabric of empty space itself. Think of the vacuum of space not as true nothingness, but as a seething foam of virtual particles that constantly flicker in and out of existence. This quantum jitter endows every cubic centimeter of empty space with a tiny, repulsive energy. Across the vast emptiness of the cosmos, this tiny push adds up to an unstoppable force. As the universe expands and creates more space, it creates more of this repulsive energy, leading to a runaway acceleration. The implications are as profound as they are unsettling. What does it mean for the ultimate fate of the cosmos if this acceleration continues unchecked? To answer that, we must peer into the vacuum and ask a deceptively simple question. What is the true nature of nothing? The vacuum of space is not a true void. It is a seething ocean of quantum potential, where virtual particles flicker into and out of existence in a relentless, chaotic dance. This is the concept of vacuum energy, a fundamental prediction of quantum field theory. Empty space itself possesses a tiny, intrinsic energy. Yet this beautiful idea leads directly to the most embarrassing failure in all of theoretical physics, a problem so severe it is known as the vacuum catastrophe. When physicists attempt to calculate the energy density of this quantum vacuum, the number they get is absurd. It is 10 to the power of 120 times larger than the value we actually observe for dark energy. To grasp the magnitude of this error, imagine calculating the weight of all the water in the Earth's oceans, and your answer comes back greater than the mass of the entire observable universe. It is not even close. This is not a small rounding error. It is a screaming alarm that our two most successful theories, quantum mechanics and general relativity, are fundamentally incompatible when it comes to describing the nature of nothing. Theorists have wrestled with this catastrophe for decades. Some hoped that a theory called supersymmetry would cancel out the contributions of these virtual particles, bringing the predicted value down to a reasonable level. But experiments at the Large Hadron Collider have found no evidence for supersymmetry where it was most needed. Others resort to the anthropic principle, a controversial idea suggesting that the value of the cosmological constant must be small for life to exist, and we simply happen to live in one of the rare universes where that is true. This feels to many like giving up on a fundamental explanation. The sheer scale of this failure forces a humbling question. Could dark energy be something more dynamic than Einstein's static cosmological constant? This idea is called quintessence, a name borrowed from the ancient element for the substance of the heavens. Quintessence proposes that dark energy is not a fixed property of the vacuum, but a dynamic field that changes over time. It could be a fifth fundamental force, one that slowly evolves, perhaps growing stronger or weaker as the cosmos ages. This would mean the acceleration of the universe is not a permanent, foregone conclusion. What does it say about our quest for knowledge that our most brilliant calculations can be so spectacularly wrong about the energy of nothingness? This vacuum catastrophe is a stark reminder that we are still peering through a glass, darkly, and the greatest mysteries of the cosmos may require us to rethink the very meaning of reality itself. Einstein's cosmological constant was a fixed feature, a permanent fixture of empty space. But what if the engine of cosmic expansion is not so steady? This is the radical proposal of quintessence, a theory that reimagines dark energy as a dynamic, evolving field, a kind of fluid that permeates all of reality. Unlike the static cosmological constant, a quintessence field can change in strength over time, ebbing and flowing across the eons. This idea offers a potential escape from the fine-tuning problem, the inexplicable coincidence that the cosmological constant has the incredibly small, specific value needed for our universe to exist. With quintessence, the strength of dark energy is not a fixed number but the outcome of a dynamic process. It could have been much stronger in the past or could weaken in the future. There are models where this field acts as an attractive force, similar to gravity, and others where it remains repulsive, but its power shifts. The key to testing this lies in measuring the history of the universe's expansion with exquisite precision. Scientists characterize dark energy by its equation of state, a parameter called W. For a pure cosmological constant, W is exactly -1. If observations ever find that W deviates from this value, even slightly, it would be a monumental discovery, a clear sign that dark energy is dynamic. A particularly elegant version of quintessence involves tracker solutions. In these models, the energy density of the quintessence field naturally follows or tracks the density of the dominant component of the universe, whether it was radiation in the earliest epochs or matter later on. For billions of years, it would have remained a minor background player hiding in plain sight. Only recently, as the universe expanded and matter thinned out, would this tracker field have emerged to dominate the cosmos and begin its accelerated expansion. Some cosmologists find this a more natural narrative than a cosmological constant that was inexplicably dormant for 99% of cosmic history. Yet the evidence for a simple, unchanging constant remains strong. Current data from telescopes like Planck and the Dark Energy Survey consistently point to a value of W very close to -1. The question then becomes a profound one. Which vision of the cosmos is more unsettling? A universe doomed by a permanent, immutable force that will eventually tear apart every structure, or one governed by a dynamic energy that could, in principle, change its mind, potentially leading to a future we cannot even predict. The search for an answer is driving the design of a new generation of observatories, machines that will map the history of expansion with unprecedented detail, hoping to catch dark energy in the act of being something more than just a constant. From a humble observatory on Mount Wilson, Edwin Hubble first glimpsed the cosmic drift. By meticulously observing the faint glow of distant galaxies, he discovered their light was stretched, reddened, as if the very fabric of space between us was stretching. The universe was not static but expanding, a revolutionary idea that forever changed our place in the cosmos. Decades later, that discovery would be overturned once more, revealing an expansion that was not just continuing but accelerating. Pinpointing the exact rate of this expansion, a number called the Hubble constant, has become one of the most heroic and frustrating quests in all of science. It is a number that holds the key to the universe's age, its size, and its ultimate fate. To measure it, astronomers rely on cosmic lighthouses, objects with a known intrinsic brightness called standard candles. By seeing how dim these candles appear across the void, we can calculate their distance. The original standard candles were Cepheid variable stars, pulsating giants whose rhythm reveals their true brightness. Hubble used them. Today, we use them with far greater precision, but we have added a more powerful tool, the Type 1, a supernova. These titanic stellar explosions are so brilliantly consistent they can be seen across billions of light years. The Hubble Space Telescope became a master of this cosmic cartography. For over 30 years, its sharp eyes above the blurring atmosphere have peered into distant galaxies, finding both Cepheids and supernova to build a cosmic distance ladder, rung by painstaking rung. One team, known as SH0ES, has dedicated itself to this task. Their work is a lesson in meticulous calibration, measuring the flicker of Cepheids in galaxy after galaxy, then using those to calibrate the flash of supernova even farther out. The result is a measurement of the Hubble constant with a stunningly small margin of error. Yet, this is where the mystery deepens. When we measure the expansion rate using these local, late universe methods, we get one number. But when we use a different technique, looking at the very early universe imprinted in the cosmic microwave background, we get a different, slightly slower number. This discrepancy is the Hubble tension. It is not a small statistical fluke. It is a stubborn gap that has persisted despite years of improved data and analysis. As one project scientist put it, we are not just arguing over decimal points anymore. We are checking and rechecking our work, and the disagreement will not go away. This tension suggests a crack in our standard model of cosmology. Perhaps dark energy is not constant but evolving, as the quintessence theory proposes. Or perhaps dark matter has properties we have not yet accounted for. It might even be a sign of something entirely new, a particle that existed in the early universe and changed its fundamental physics. The next generation of telescopes is being built to solve this riddle. The Nancy Grace Roman Space Telescope, set to be Hubble's powerful successor, will not just look at a few galaxies but will conduct a vast survey of the cosmos. It will map the universe in 3 dimensions, using not only supernova but also another powerful tool called Baryon acoustic oscillations. These are fossilized sound waves from the early universe, frozen into the distribution of galaxies, acting as a standard ruler across cosmic time. By comparing this detailed modern map with the ancient snapshot from the cosmic microwave background, we will strain to see what is pulling these measurements apart. The Hubble constant is more than a number. It is the universe's most vital sign, and the fact that we cannot agree on its value tells us that the veil over the cosmos may be hiding not just dark forces, but entirely new laws of physics waiting to be discovered. A master clockmaker finds his 2 most trusted clocks, each a marvel of precision, ticking at undeniably different rates. This is the profound unease astronomers feel with the Hubble tension. It is not a minor quibble but a persistent discrepancy that strikes at the heart of our cosmic model. On one hand, we have the early universe's baby picture, the cosmic microwave background, as exquisitely mapped by the Planck satellite. This primordial snapshot allows us to project forward, using our standard model of cosmology, to predict the universe's expansion rate today. On the other hand, we have direct measurements from the local universe, where the Hubble Space Telescope painstakingly observes the rhythmic pulse of Cepheid variable stars and the brilliant flash of Type I, a supernova, to gauge cosmic distances and speeds. These 2 methods, each incredibly precise in its own right, yield answers that stubbornly refuse to agree. The local measurement suggests an expansion that is faster, by a significant margin, than the one extrapolated from the ancient past. This is not an error that fades with better data. In fact, as our instruments have sharpened, the statistical significance of this gap has only grown, reaching a level that is now almost impossible to dismiss as simple chance. The implication is staggering. Our foundational model of the cosmos, known as lambda CDM, which is built upon the pillars of dark energy and cold dark matter, might be incomplete. Leading cosmologists are now exploring radical fixes to mend this crack. Some propose an injection of early dark energy, a transient repulsive force that briefly surged in the universe's first moments, altering its initial conditions just enough to explain the faster expansion we see today. Others investigate the possibility that neutrinos, those ghostly particles that stream through everything, have exotic, unknown properties that could have subtly shifted the cosmic evolution. Modifications to the laws of gravity itself are also back on the table. The Hubble tension is not alone. It is the most prominent of several growing anomalies. There is the sigma-8 tension concerning how clumpy matter is in the nearby universe versus predictions. There is the curious problem of the lensing amplitude in the cosmic microwave background, which seems a bit too strong. Individually, each could be a fluke. Collectively, they point towards a potential paradigm shift. Are we witnessing the first tremors of a scientific revolution, one that will force us to rewrite the opening chapters of our cosmic story? This crack in our model does not point forward but backward, inviting us to re-examine the very first moments of everything. 380,000 years after the Big Bang, the universe finally took its first clear breath. Before that moment, it was an opaque, seething plasma, a dense fog of particles and energy where light could not travel freely, constantly scattering off a soup of free electrons. But as the cosmos expanded and cooled, a pivotal event called recombination occurred. Electrons were finally captured by protons, forming the first stable atoms, primarily hydrogen. In that instant, the fog lifted. The universe became transparent, and that first burst of light released from its prison has been traveling across the cosmos ever since. We see it today as the cosmic microwave background, a faint, cold glow bathing the entire sky. It is the oldest fossil we will ever observe, the afterglow of creation itself. This relic radiation was predicted by theory but discovered entirely by accident in 1964 by Arno Penzias and Robert Wilson, who initially mistook the persistent hiss in their radio antenna for pigeon droppings. That static was the echo of the universe's birth. Since then, a series of extraordinary satellites have transformed that faint hiss into our most detailed map of the infant cosmos. The Decode satellite first confirmed the cosmic microwave background had a nearly perfect blackbody spectrum, the hallmark of radiation released from a hot, dense state. Its successor, WMAP, provided a sharper image, and the Planck mission delivered the most exquisite baby picture of the universe ever taken. The map it produced looks like a splotchy oval, a cosmic Jackson Pollock painting in shades of blue and red. But those splotches are not random. They represent tiny variations in temperature, fluctuations of just 1 part in 100,000. These are the seeds of destiny. Slightly denser regions, shown as cooler blue patches, held the extra gravitational tug of dark matter, the anchors that would eventually pull in ordinary matter and ignite the first stars, building the galaxies we see today. The precise patterns in this map are a treasure trove of information. Scientists analyze what is called the power spectrum of the cosmic microwave background, a graph that reveals a series of prominent peaks, like the harmonic notes of a cosmic chord struck at the moment of recombination. The scale and position of these acoustic peaks act as a supreme cosmic ruler. They allow cosmologists to measure the geometry of the universe, its total density, and its composition with unparalleled precision. It is from these peaks that we derive our gold standard numbers, the recipe for the cosmos: 27% dark matter, 68% dark energy, and just 5% ordinary matter. The cosmic microwave background holds even deeper secrets. Its light is not just hot or cold, it is also polarized, meaning its waves vibrate in a preferred direction. This polarization carries an imprint of the universe's final moments before transparency, recording the last frantic scattering of photons. Most intriguingly, one specific pattern within this polarization, known as a B mode, could be the smoking gun for gravitational waves generated during a period of hyper-expansion in the very first fraction of a second after the Big Bang, a theory called inflation. Finding that specific curl in the polarization would be like discovering the fossilized ripples from the birth of spacetime. This ancient light is therefore more than a snapshot. It is a full diagnostic of the cosmos, confirming the existence of dark matter and dark energy while simultaneously hinting at the physics of the absolute beginning. Every time we point a telescope at this cold microwave glow, we are reading the opening lines of our cosmic story, written in the faint whisper of the universe's first dawn. The cosmic microwave background is a perfect snapshot of a 380,000-year-old universe, but it presents two profound puzzles that the original Big Bang theory simply could not answer. The first is the horizon problem. When we look at the cosmic microwave background in opposite directions in the sky, those regions have exactly the same temperature. This is deeply strange because in the standard Big Bang model, those two patches had not had enough time since the beginning to exchange heat or information. They were forever beyond each other's cosmic horizon, like two strangers on opposite sides of the world who somehow decide to wear the exact same outfit. The second puzzle is the flatness problem. The geometry of our universe is incredibly flat, like a perfectly stretched sheet. Yet the equations showed that any tiny deviation from perfect flatness in the early universe should have been wildly amplified over time, leading to a cosmos that either quickly collapsed back on itself or expanded into a barren void. For our universe to be so flat today, its initial conditions had to be fine-tuned to an astonishing degree of precision, like balancing a pencil on its tip for billions of years. These were not minor issues, they were cracks in the foundation. The solution came in a flash of insight, a theory called cosmic inflation. Proposed by Alan Guth and others, it suggests that in the very first fraction of a second, the universe underwent a period of exponentially rapid expansion, inflating from a subatomic speck to something macroscopic faster than the speed of light. This was not an expansion of matter into space, but a stretching of space itself. The driver of this incredible growth was a peculiar energy field dubbed the inflaton. Think of the infant universe as a tiny, crumpled ball of paper, wrinkled with chaotic energy. Inflation is like blowing that paper up to the size of an entire continent. All the original wrinkles and crumples are stretched out into vast, gentle hills and valleys. This single, elegant idea solves both puzzles at once. The entire observable universe was once a tiny, connected region that was smoothed to a uniform temperature before inflation blew it up, explaining the horizon problem. And the phenomenal stretching forced the geometry of the cosmos toward flatness, just as inflating a balloon makes its surface appear flatter and flatter, solving the flatness problem. But inflation did something even more remarkable. It took the microscopic quantum jitters, the inherent uncertainty of the inflaton field, and stretched them to cosmic proportions. These tiny quantum fluctuations became the grand density variations, the seeds for all future structure. The slightly denser regions seen as cool spots in the cosmic microwave background, the very anchors for galaxies, were born from quantum fuzz magnified by inflation. The hunt for direct proof of inflation is one of cosmology's grandest quests. Theorists like Andre Linde, who developed many of the key models, speak of its breathtaking predictive power. The most sought-after evidence is a specific signature imprinted on the cosmic microwave background's polarization, a swirling pattern known as B modes. These would be the fossilized ripples, the gravitational waves, generated by the violent throes of inflation itself. Finding them would be like hearing the echo of the universe's first cry. Experiments at the South Pole, like BICEP and the upcoming Simons Observatory, scan the pristine polar skies for this faint curl in the ancient light. They operate in one of the coldest, driest places on Earth, where the atmosphere is too thin to block our view of the microwave background. There are many models of inflation, from chaotic to eternal, each with different implications for the initial conditions and the ultimate fate of the cosmos. Yet they all share this core narrative of a spectacular beginning. This explosive stretch set the initial conditions for everything that followed, creating the smooth, flat stage upon which dark matter and dark energy would later emerge to direct the cosmic play. The search for its final confirmation continues at the bottom of the world, in the silent, frozen air where the universe's first whispers are still faintly heard. Our universe might not be unique, but merely a single bubble in an infinite, frothing cosmic foam. This is the staggering possibility of the multiverse, a concept that emerges naturally from the mathematics of eternal inflation. If the inflaton field could kickstart a period of hyper-expansion in our region of spacetime, there is no reason it could not happen elsewhere, again and again. The process would be eternal, continuously spawning new pocket universes within an ever-expanding meta-universe. Each of these bubbles could have wildly different properties, a unique combination of physical constants and fundamental laws. The force we call dark energy, with its curiously small value, might not be a fundamental law at all. In a multiverse, it could simply be a local environmental accident. We find ourselves in a bubble where the cosmological constant is just right for galaxies to form and life to emerge, a stark example of the anthropic principle. As physicist Leonard Susskind has argued, this provides a potential escape from the vacuum catastrophe, not by explaining why the dark energy value is small, but by explaining why we observe it to be small. We are here because this is one of the rare, life-friendly bubbles. This idea connects to the vast theoretical landscape of string theory, which suggests an almost unimaginable number of possible vacuum states, each corresponding to a different universe with its own physics. The multiverse is not a single idea but a spectrum of concepts. There is the inflationary multiverse of bubbling domains. There is the quantum many-worlds interpretation, where every quantum decision branches reality into new parallel timelines. There is even the mathematical multiverse, which suggests that every mathematically consistent structure might physically exist somewhere. Picture a boundless ocean under an endless sky. Each island in this ocean is a separate universe with its own climate, its own geology, its own rules. Some islands are barren rocks, their physical laws too hostile for any complex structure. Others are gaseous worlds without form. We simply live on a rare, temperate island where the conditions are just right for trees to grow and life to flourish. We cannot sail to the other islands, for the space between them inflates faster than any signal can cross. Critics, however, voice a deep concern. They argue that if these other universes are permanently causally disconnected from our own, then the multiverse hypothesis moves beyond the realm of testable, falsifiable science. It becomes a metaphysical assumption. Does this concept genuinely solve the fundamental mysteries of dark energy and fine-tuning, or does it merely explain them away by invoking an infinite number of unseen worlds? This is the razor's edge of modern cosmology, a frontier where the quest to decode the universe's darkest energies pushes us to contemplate realities beyond our own, forcing us to ask what it even means for an idea to be scientific. On September 14, 2015, a ripple in the fabric of spacetime caused by two black holes colliding over 1 billion light-years away was felt on Earth. The Laser Interferometer Gravitational Wave Observatory, or LIGO, had made the first direct detection of gravitational waves, confirming a century-old prediction of Einstein's theory and opening an entirely new sense with which to perceive the cosmos. This was the birth of gravitational wave astronomy, a revolution that allows us to hear the universe. For all of human history, our knowledge of the cosmos came from light, from the photons that travel across space to our telescopes. But light can be blocked, absorbed, or scattered. Gravitational waves are distortions in spacetime itself, and they pass through matter almost completely unimpeded. They are a pure messenger from the most cataclysmic events in existence. These waves are generated when massive objects accelerate, much like a moving boat creates ripples on a pond. The most powerful sources are the inspirals and mergers of incredibly dense objects, like black holes and neutron stars. The first detected signal was a distinctive chirp, the sound of two black holes, each dozens of times the mass of our Sun, spiraling into each other at nearly the speed of light and merging into one. Since that first detection, our new sense has revealed a universe far more dynamic and violent than we knew. We have heard the collisions of numerous black hole pairs, and in a landmark event in 2017, we witnessed the merger of two neutron stars. This event, catalogued as GW170817, was a watershed moment. For the first time, a cosmic event was seen and heard. Gravitational wave observatories detected the chirp, and within hours, telescopes across the globe and in space swiveled to observe the resulting flash of light across the electromagnetic spectrum, from gamma rays to radio waves. This multi-messenger event was like watching a silent movie and suddenly getting the soundtrack. It provided a crucial, independent measurement of the Hubble constant. By comparing the distance inferred from the gravitational wave signal to the redshift of the host galaxy, astronomers could calculate the universe's expansion rate without relying on the traditional cosmic distance ladder. This new method is still in its infancy, but it promises to help resolve the persistent Hubble tension. The future of this field is even more breathtaking. Projects like the space-based Laser Interferometer Space Antenna, or LISA, will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart. Free from the seismic noise of Earth, LISA will detect low-frequency gravitational waves that are impossible to sense from the ground. It will listen for the mergers of supermassive black holes, the monstrous engines at the hearts of galaxies, as they spiral together over millions of years. This will allow us to map the history of cosmic expansion in a completely new way, offering fresh constraints on the nature of dark energy. As one LIGO researcher famously said, "We are not just looking up at the sky anymore, we are listening to it." We can now hear the faint drumbeats of cosmic collisions, the low hum of binary white dwarfs, and perhaps one day the faintest whisper of all, the primordial gravitational waves from the first frantic moments after the Big Bang. This new sense is tuning our ears to the hidden symphony of the cosmos, a symphony played on the strings of space-time itself. Trillions of invisible particles are streaming through you at this very moment, leaving no trace of their passage. These are neutrinos, nature's most elusive messengers, so ghostly that they can pass through a light year of lead without a single interaction. Born in the hearts of stars, in the fury of supernova, and in the decay of radioactive elements, they saturate the cosmos in a silent, ceaseless rain. For decades, we believed they were entirely massless cosmic spectators with no weight in the grand scheme of things. We were wrong. Neutrinos come in 3 known types or flavors: the electron neutrino, the muon neutrino, and the tau neutrino. Their deepest secret is a bizarre quantum behavior called oscillation. A neutrino produced as one flavor does not stay that way. As it travels through space, it morphs, oscillating between all 3 identities in a constant, silent dance. This strange shimmering is only possible if neutrinos have mass, a discovery that overturned a long-held pillar of physics and earned a Nobel Prize. The mass is unimaginably small, millions of times lighter than an electron, but their sheer abundance is staggering. Billions of neutrinos from the Sun pass through your thumbnail every second. When you add up all the neutrinos left over from the Big Bang, their combined gravitational influence could be enough to subtly shape the cosmos. Their impact is one of gentle resistance. In the early universe, dark matter was trying to pull matter into dense clumps to form galaxies and clusters. But neutrinos, moving at nearly the speed of light, streamed freely out of these nascent structures. They acted like a cosmic pressure, slowing the growth of the largest formations in the universe. The ghost was subtly resisting the architect. Pinning down their exact mass is one of the most pressing challenges in physics. Experiments like Katrin in Germany are monumental feats of engineering, using a giant tritium source and a spectrometer the size of a house to hunt for the faintest imprint of a neutrino's mass in the energy of decaying electrons. Cosmological surveys provide another route, scanning the large-scale structure of the universe for the specific smoothing effect that a population of light neutrinos would have imprinted. The puzzle deepens with a hypothetical fourth player, the sterile neutrino. This particle would interact only through gravity, making it a compelling, though unconfirmed, candidate for a portion of the dark matter that has eluded all other detection. The true power of these phantoms is revealed in the most violent stellar deaths. When a massive star goes supernova, the core collapses into an ultra-dense neutron star or black hole. In that cataclysm, 99% of the star's energy is not carried away by the spectacular explosion of light, but by a tremendous pulse of neutrinos. These ghost particles are the true engine of destruction, blasting outward and tearing the star apart from within. So we are left with a humbling thought. Could these tiny, almost massless entities, once dismissed as cosmic phantoms, hold a critical key to the dark universe? Their subtle gravity weaves through the cosmic web, and their ghostly presence may be written into the very blueprint of existence. Stretching across billions of light years, the universe reveals an architecture of breathtaking complexity and beauty. This is the cosmic web, the largest structure we know, a delicate tracery of glittering galaxy filaments surrounding vast, empty voids. It looks like the froth on an ocean of nothingness, a network of interconnected knots and threads. This grand design is not a random scattering. It is the direct and precise imprint of those tiny density fluctuations from the primordial universe, the ones we see in the cosmic microwave background, amplified over eons by the relentless gravitational pull of dark matter. The dark matter acted as a cosmic blueprint, its invisible mass defining the valleys where galaxies would eventually bloom. At the intersections of these great filaments where the dark matter is densest, immense halos form. These are the gravitational hubs of the universe, ordinary gas pulled by the irresistible tug of this unseen scaffold, flows along the dark matter filaments like water converging in river deltas. This gas pools at the nodes, fueling the birth of stars and the growth of brilliant galaxy clusters. The entire process is a cosmic feeding frenzy, directed by a ghostly hand. To map this invisible architecture, astronomers conduct monumental surveys of the sky. Projects like the Sloan Digital Sky Survey have painstakingly measured the positions and redshifts of millions of galaxies. Redshift, the stretching of a galaxy's light toward the red end of the spectrum caused by the universe's expansion, tells us not only how far away a galaxy is but also its velocity. By plotting millions of these galaxies in 3 dimensions, we get a tomographic map of the cosmos, revealing the Webb's spine of dark matter. Upcoming instruments like the Dark Energy Spectroscopic Instrument, or DESI, are taking this cartography to a new level. They will map tens of millions of galaxies and quasars, creating the most detailed 3-dimensional atlas of the universe ever made. These maps are not just pretty pictures. They are rigorous tests of our fundamental physics. The geometry of the web, the thickness of its filaments, and the sizes of its voids are all shaped by the balance between the gravitational pull of dark matter and the repulsive push of dark energy. Astronomers use subtle clues within the map, like redshift space distortions, to probe the growth rate of cosmic structure. This effect occurs because a galaxy's measured redshift is a combination of the universe's expansion and its own peculiar motion as it falls into the Webb's gravitational wells. This creates a distinct squashing effect in the map, allowing scientists to measure how quickly structures are clumping together over time. If dark energy is indeed constant, it should be slowly applying a brake to this growth. If the growth rate is different than predicted, it could mean dark energy is dynamic, changing the cosmic contest between attraction and repulsion. The visualizations from these surveys are humbling. They show a universe that is bubbly and interconnected, a sponge-like structure where each glowing filament is a highway of billions of galaxies. and each dark void is a desolate expanse that could take hundreds of millions of years to cross at the speed of light. This is the ultimate expression of dark matter's silent, organizing power. We are not just mapping stars, we are charting the hidden continents of the cosmos, tracing the gravitational skeleton that gives the universe its form and its fate. The faint whisper of the cosmic microwave background carries a fossilized echo, a sound wave frozen in time. In the universe's first few 100,000 years, it was a seething, opaque plasma, a hot soup of atomic nuclei, electrons, and light. In this dense fluid, gravity acted as a constant pull, trying to draw the dark matter and the baryonic matter together into denser clumps. But this inward tug was counteracted by an immense outward pressure from the intense radiation. This push and pull created sound waves, spherical pressure fronts that rippled outward through the primordial plasma at over half the speed of light. Then, in an instant, the universe cooled enough for atoms to form. The fog cleared, the radiation flew free, and the pressure vanished. The sound waves stopped in their tracks, freezing these spherical ripples of matter into the fabric of the cosmos. Today, we see the imprint of these waves as a subtle, preferred scale in the distribution of galaxies. This is the Baryon acoustic oscillation, a cosmic standard ruler etched across the sky. The radius of that frozen spherical shell is about 500 million light-years across. By finding this specific scale in the distribution of galaxies at different distances, we can measure how much the universe has stretched over billions of years. It is like having a ruler of known length and watching how its apparent size changes as we look deeper into the past. Cosmologists prize this measurement for its incredible cleanliness. Unlike supernova measurements, which can be affected by interstellar dust or the inherent variations in the explosions themselves, the BAO scale is a statistical feature imprinted on the large-scale structure of the universe. It is immune to many of the systematic errors that plague other methods. This robustness makes it one of our most powerful and direct tools for probing the history of cosmic expansion and the nature of dark energy. To map this fossilized sound wave, astronomers are undertaking monumental surveys of the cosmos. The Dark Energy Spectroscopic Instrument, or DESI, is at the forefront of this effort. Perched atop a telescope in Arizona, DESI is not taking pretty pictures of galaxies. It is precisely measuring their spectra, the fingerprint of their light, for tens of millions of galaxies. By obtaining the redshift for each one, it can place them in a three-dimensional map of the universe, revealing the subtle over-densities where galaxies are more likely to be found separated by that 500 million light-year scale. Imagine finding perfectly preserved bubbles of a specific size in different layers of ancient rock. By measuring how much those bubbles are stretched in the older, deeper layers, you could calculate exactly how much the Earth's crust has expanded over the eons. The BAO signal works in precisely this way. As we look out to greater distances and thus further back in time, we measure the apparent size of this standard ruler. If dark energy is a constant cosmological force, the ruler's growth will follow one specific path. If dark energy is dynamic, changing its strength over time, the growth will deviate, revealing a different cosmic history. The data from these ambitious surveys is now pouring in, offering a clear, precise echo from the dawn of time to measure the dark force shaping our future. 570 million pixels stared into the southern sky for 6 years, gathering light from a realm of ancient ghosts. The Dark Energy Survey was a monumental census of the cosmos, an international collaboration that mapped hundreds of millions of galaxies across 1/8 of the visible sky. Its home was the Blanco telescope in the clear, dry air of the Chilean Andes, a mechanical behemoth armed with a digital eye of staggering precision. The data it collected was a deluge, a flood of light captured in petabytes of digital images. To process this torrent, scientists built complex algorithms to find, measure, and classify the shapes and distances of galaxies so faint they were little more than smudges of light on a sensor. This was not a quest for pretty pictures, but a forensic investigation of dark energy, pursued with 4 distinct and powerful lines of inquiry. The first was weak gravitational lensing, the subtle warping of distant galaxy shapes by the invisible mass of dark matter that light must pass on its journey to us. It is an effect so minuscule it is statistically invisible in a single galaxy, but across millions, a coherent distortion emerges, a telltale shear that reveals the hidden architecture of the cosmos. A scientist on the project described the immense challenge, explaining that they had to understand the telescope's own optical distortions and the sensor's electronic quirks better than anyone ever had before. They were measuring shape changes smaller than 1%, and any instrumental error could easily drown out the cosmic signal they sought. The second method was galaxy clustering, charting the immense 3-dimensional map of the universe to find the frozen sound waves of Baryon acoustic oscillations, that standard ruler imprinted in the early universe. The third was galaxy cluster counts, because the number of these massive structures found at different distances is a sensitive probe of how quickly the universe was clumping together under gravity's pull, a growth rate that dark energy suppresses. And the fourth was the tried and true method of Type 1, a supernova, using these standard candles to measure the expansion history directly. The result of this multi-pronged assault was a set of the most precise measurements ever made of the cosmos's fundamental ingredients. The Dark Energy Survey delivered a razor-sharp value for the universe's matter density and placed a tight constraint on how clumpy that matter is, a parameter known as sigma 8. When the weak lensing data was processed, it allowed the team to create stunning maps of the invisible. These were not images of light, but charts of gravitational pull, revealing the dark matter scaffolding in exquisite detail, with vast filaments connecting brilliant knots where massive galaxy clusters shone. This digital sky survey marked a paradigm shift, a new era where cosmology is driven by immense data sets and statistical power. The legacy catalog it produced is a treasure trove that will be mined for years, but it also clearly set the stage for its even more powerful successors, proving that to unravel the darkest secrets of the universe, we must first learn to measure its faintest whispers. High on a mountain peak in Chile, a new eye is preparing to open, one that will not merely glimpse the cosmos but watch its every breath. The Vera C. Rubin Observatory represents a quantum leap in our ability to observe the universe, a facility designed to conduct a 10-year cinematic survey of the sky called the Legacy Survey of Space and Time. Its heart is a 3-mirror telescope with an 8.4-meter primary mirror, coupled with the largest digital camera ever constructed, a 3.2 gigapixel behemoth. This incredible instrument will photograph the entire visible southern sky every few nights, creating a deep, time-lapse movie of the heavens. It will not just see the static universe, but the dynamic one, capturing any flicker of change across an immense volume of space. The goals of this monumental survey are almost boundless. It is projected to catalog over 20 billion galaxies and a similar number of stars, discover millions of supernovae, and map our solar system in unprecedented detail, finding countless new asteroids and distant icy worlds. For the dark universe, this survey is a revolution in waiting. It will attack the mystery of dark energy with all 4 primary methods at once, but with a statistical power that dwarfs all previous efforts combined. Its weak gravitational lensing map will be so detailed it will trace the distribution of dark matter with exquisite precision, revealing the subtle distortions in billions of galaxy shapes. It will measure the Baryon acoustic oscillation scale with tens of millions of galaxies, providing a supremely accurate ruler to track the expansion history. It will find so many Type 1 a supernova that it will chart the acceleration of the universe across cosmic time with minimal uncertainty, and it will count galaxy clusters in such vast numbers that the growth of cosmic structure will be laid bare. The scale of the data is itself a cosmic challenge. The observatory will generate over 20 terabytes of data each night, amounting to more than 200,000 images. Over the full decade, it will produce a catalog hundreds of times larger than any that has come before. Processing this deluge requires a new kind of astronomy, one fueled by immense computing power and sophisticated machine learning algorithms to spot the subtle patterns hidden within. Scientists speak of this project with a palpable sense of anticipation. They expect it to not just refine our measurements, but to potentially crack open the nature of dark energy, revealing whether it is truly a constant or something dynamic and evolving. It could finally pinpoint the properties of dark matter by watching how it sculpts galaxies on the finest scales, and with its relentless watchfulness, it is almost certain to detect entirely new phenomena, things that flicker and move in the night sky that we have never had the speed or sensitivity to see before. This observatory will transform the static sky into a living, breathing entity, and in its motion we may finally find the keys to the dark forces that command it. A profound cosmic surprise was waiting in the very first images from the James Webb Space Telescope. Instead of a sparse collection of faint, infant galaxies at the edge of time, JWST revealed a universe already teeming with massive, mature systems, galaxies that seemed to have formed with impossible speed. This was not what many models, built upon the steady hand of cold dark matter, had predicted. The James Webb is far more than a successor to Hubble. It is a time machine designed for the infrared, a window into an era when the universe was stretching the light from its first stars and galaxies into the long, red wavelengths that are invisible to our eyes. Its immense gold-coated mirror and suite of hypersensitive instruments are built to capture this ancient, redshifted glow, to see the cosmic dawn itself. One of its primary missions is to witness the epoch of reionization, that pivotal period when the first brilliant objects burned away the primordial hydrogen fog that filled the cosmos, turning the universe transparent once and for all. By staring for days into tiny, seemingly empty patches of sky, its deep-field observations pull back the curtain on this transformative age. The sheer number and size of the galaxies it finds there is sending shockwaves through cosmology. How could such vast structures assemble so quickly after the Big Bang? The process of galaxy formation is a delicate dance directed by dark matter. Its invisible halos provide the gravitational wells for gas to collapse and stars to ignite. The cold dark matter paradigm, which posits slow-moving particles, has been spectacularly successful at building the universe we see around us today. But the James Webb's view of the infant cosmos is posing a sharp new test. Finding massive, fully formed galaxies in the universe's first few 100 million years is like walking into a nursery and finding toddlers already reading novels. It suggests that either star formation was astonishingly efficient in the early universe, or that our understanding of the dark matter scaffolding itself needs adjustment. Perhaps dark matter is not perfectly cold but slightly warm, giving it a small thermal motion that could alter how quickly the first small structures form. Or maybe the physics of those first stars was radically different. As one astonished astronomer noted upon seeing the data, the models were not just slightly off, they were missing something fundamental about the universe's frantic childhood. Beyond rewriting the first chapters of cosmic history, JWST is also revolutionizing our search for life's ingredients. It analyzes the atmospheres of distant exoplanets by capturing the faint starlight that filters through their air. By splitting this light into a spectrum, it can identify the chemical fingerprints of water vapor, methane, and carbon dioxide, mapping the climate of worlds hundreds of light years away. It peers into the dusty nurseries where stars and planets are born, revealing the intricate structures that will one day become solar systems like our own. Every new image is a data point in our grand cosmic inventory, a measurement that helps us understand the balance between the dark and the light. The telescope's findings are not merely adding details to our story, they are forcing a re-examination of its foundational plot. What other secrets are waiting in that ancient infrared glow, ready to challenge our most deeply held ideas about the dark universe? While the James Webb peers into the cosmic dawn, another space telescope has begun a panoramic survey of the dark present. The European Space Agency's Euclid mission is an observatory with a single, profound purpose: to map the invisible architecture of the universe. Unlike telescopes that study specific, brilliant objects, Euclid is a cosmic cartographer, designed to meticulously chart the shapes and positions of over 1 billion galaxies across a staggering 1/3 of the entire sky. Its mission is to construct the largest and most accurate three-dimensional map of the cosmos ever made, a map where the real landmarks are not stars, but the subtle fingerprints of dark matter and dark energy. To achieve this, Euclid is equipped with two powerful instruments working in perfect synchrony. A visible wavelength imager captures the ultra-sharp shapes of galaxies, while a near-infrared spectrometer and photometer precisely measures their redshifts, telling us their distances. This combination of shape and distance data for such an immense number of galaxies is the key to unlocking the dark universe. The central technique is weak gravitational lensing, the tiny, almost imperceptible warping of a galaxy's shape caused by the gravitational pull of dark matter that lies between it and us. Individually, this distortion is minuscule, but by measuring the coherent patterns of distortion, or cosmic shear, across billions of galaxies, Euclid can trace the vast, web-like distribution of the invisible dark matter scaffolding. It is like looking at a cityscape through a wavy pane of glass, and from the precise distortions of every distant light, inferring the exact shape of the invisible glass itself. At the same time, by plotting the precise three-dimensional positions of these galaxies, Euclid will track the history of the universe's expansion through Baryon acoustic oscillations, the frozen sound waves from the Big Bang. This will allow scientists to measure the relentless push of dark energy with unprecedented precision, constraining its equation of state, the parameter that reveals whether it is a simple cosmological constant or something more dynamic and strange. The technical precision required for this is almost beyond belief. To ensure its measurements are not corrupted by the slightest instrumental drift, the telescope's entire structure must be kept at a thermal stability within a few millionths of a degree. This incredible steadiness, combined with its location far above the blurring effects of Earth's atmosphere, gives Euclid a razor-sharp view across billions of light years. The data now streaming back is not just a catalogue of lights in the sky. It is a forensic dataset, a record of the gravitational tides and the expansion history that have been dictated by the dark components for billions of years. We are no longer just looking at the universe, we are learning to read its hidden blueprints. The Nancy Grace Roman Space Telescope sees the cosmos with a new kind of vision. It combines the razor-sharp clarity of Hubble with a field of view 100 times larger, allowing it to capture the grandeur of deep space in sweeping, cinematic panoramas. Named for the pioneering astronomer who paved the way for NASA's exploration of the cosmos, this observatory is a cosmic census taker on an epic scale. Its primary mission is to conduct a high-latitude survey, a deep and wide map of the sky designed to measure the subtle fingerprints of dark energy. It will use two powerful techniques in tandem. The first is weak gravitational lensing, measuring the tiny distortions in the shapes of over 100 million galaxies to trace the invisible distribution of dark matter. The second is galaxy clustering, mapping the positions of billions of galaxies to find the frozen sound waves of Baryon acoustic oscillations. Together, these measurements will track the growth of cosmic structure across billions of years with phenomenal precision, revealing how dark energy has been suppressing the clumping of matter over time. But Roman's vision extends beyond dark energy. It will also conduct a monumental search for stellar explosions, discovering thousands of Type 1, a supernova, to independently chart the universe's expansion history. The sheer statistical power of this survey will shrink our measurement errors to a whisper, offering a definitive look at the acceleration of the cosmos. The telescope's capabilities do not end there. A sophisticated coronagraph instrument will block the blinding light of nearby stars, allowing Roman to directly image and analyze the atmospheres of giant exoplanets, worlds orbiting other suns. This mission is designed for synergy. It will work in concert with the deep, focused gaze of the James Webb Space Telescope and the relentless, all-sky watch of the Vera Rubin Observatory. Roman will provide the crucial, exquisitely detailed wide-area data that connects deep field studies to the broader universe, and it will identify countless intriguing targets for Webb's powerful instruments to scrutinize in profound detail. By taking a monumental census of the infrared sky, the Nancy Grace Roman Space Telescope will produce a legacy dataset, a treasure trove that will fuel the discoveries of a generation of cosmologists and redefine our place in the dark universe. Scattered across two continents, a forest of metal ears is preparing to listen to the birth of the cosmos. The square-kilometer array is not a single telescope, but a colossal network of radio antennas being built across the vast, radio-quiet deserts of South Africa and Western Australia. When complete, its combined collecting area will span, as the name suggests, approximately 1 square kilometer, creating an instrument of almost unimaginable sensitivity. It will be so powerful it could detect an airport radar on a planet dozens of light years away. Its primary mission is to tune into the faintest radio whispers from the universe's infancy, a period known as the Cosmic Dawn. To do this, it will hunt for a specific, ancient signal, the faint emission from neutral hydrogen gas at a wavelength of 21 centimeters. This hydrogen was the raw material of the first stars and galaxies, and by mapping its distribution across the sky and back through time, the square-kilometer array will essentially create a three-dimensional movie of the universe's first billion years. We will be able to watch as the first stars ignite, their intense ultraviolet radiation slowly burning away the primordial hydrogen fog in a process called reionization. This transformation, this cosmic dawn, was driven by the gravitational pull of dark matter, which gathered the gas into the first structures. By tracing the hydrogen, the square-kilometer array will indirectly map the dark matter scaffolding that orchestrated the entire event, probing its properties and influence with a clarity never before possible. The science goals extend far beyond this cosmic origin story. The array will put Einstein's theory of gravity through its most rigorous test yet, precisely tracking the motions of pulsars, the cosmic lighthouses left behind by supernova explosions. It will search for the ripples of gravitational waves from merging supermassive black holes by monitoring these pulsar networks. It will even map the universe's magnetic fields, tracing the invisible lines of force that weave through interstellar and intergalactic space. And of course, it will conduct one of the most comprehensive searches for extraterrestrial intelligence ever attempted, scanning the cosmos for artificial signals. The challenge is as immense as the ambition. Engineers working on the project describe a data deluge unlike anything humanity has ever faced. The telescopes will generate more data in a single day than the entire global internet currently carries. Processing this torrent requires building supercomputers and developing algorithms of staggering complexity, a digital infrastructure that is itself a frontier of innovation. The construction is happening in phases, with the first, SCA-1, already underway and demonstrating the revolutionary technology. The full array, SCA-2, will complete this intercontinental web. Imagine watching a time lapse of the early universe, seeing the first flickers of light emerge in the darkness and then spread, gradually illuminating the entire cosmic landscape. This is the promise of the square-kilometer array, to hear the faint echoes of creation and witness the moment our universe first woke up. What if the dark matter holding galaxies together is not a sea of particles, but a swarm of ancient black holes? This is the compelling possibility of primordial black holes, hypothetical objects born not from the death of stars, but in the frantic first second of the universe. In that moment of extreme density, tiny regions of space could have collapsed under their own gravity, sowing black holes directly into the fabric of the cosmos. Their predicted sizes are staggering, ranging from masses lighter than an asteroid to heavier than thousands of suns. This vast range makes them a uniquely versatile candidate for the universe's missing mass. To find these primordial relics, astronomers have become cosmic detectives, employing a suite of ingenious methods. One key technique is gravitational microlensing. If an invisible primordial black hole passes directly in front of a distant star, its gravity will act as a lens, briefly magnifying the star's light and causing it to flare. Surveys like the optical gravitational lensing experiment have scanned millions of stars for these telltale flickers. The relative lack of such events has ruled out primordial black holes making up all of dark matter across a wide range of masses, particularly those around the mass of a large planet. Another method studies the delicate dynamics of ancient star clusters. If a swarm of heavy, unseen objects were present, their gravity would disrupt the clusters, slowly tearing them apart. The fact that we see such pristine, ancient clusters places tight constraints on how many asteroid-mass primordial black holes could be hiding there. Then there is the sound of their collisions. When two primordial black holes merge, they send out ripples in space-time, gravitational waves that can be heard by observatories like LIGO and Virgo. The very first detection by LIGO in 2015 was a shock for this reason. The black holes involved were each about 30 times the mass of our Sun, far heavier than what models of stellar collapse typically produce. Their surprising mass immediately sparked a renewed, serious interest in the primordial black hole hypothesis. Could these be the ancient remnants of the Big Bang itself? The signals from such mergers would have distinctive features, potentially revealing they are not the products of dead stars but something much older. Yet, the case is far from closed. Careful analysis of the cosmic microwave background places severe limits on these objects. If too many primordial black holes existed, their voracious feeding in the early universe would have left a scorching imprint on the ancient light, an imprint we simply do not see. This evidence largely rules out primordial black holes as the sole component of dark matter for most mass ranges. As one theorist noted, the window for them to constitute all of dark matter is now a very narrow one, though a significant fraction remains possible. So we are left with a fascinating, unresolved puzzle. The hunt for these primordial ghosts adds a thrilling layer to the dark matter quest, reminding us that the answer may not be a tiny particle, but a population of cosmic fossils from the violent dawn of time. The deepest flaw in our understanding of reality is a schism at the heart of physics. For a century, our two most powerful theories have been at war. General relativity paints a beautiful picture of gravity as the curvature of space-time, perfectly describing the cosmos on its grandest scales. Quantum mechanics reveals the bizarre, probabilistic rules that govern the atomic and subatomic world. Yet every attempt to combine them to describe gravity under the quantum lens results in mathematical nonsense. This reconciliation is the single greatest unsolved problem in theoretical physics, and the search for a theory of quantum gravity has led to one of the most ambitious and controversial ideas ever conceived: string theory. This framework makes a breathtaking claim. The fundamental constituents of the universe are not zero-dimensional points like electrons or quarks. Instead, they are unimaginably tiny, vibrating loops of energy, strings. Their different vibrational modes, much like the various notes a single violin string can produce, give rise to all the different particles and forces we observe. The electron is one note, the photon is another. Gravity, through a hypothetical particle called the graviton, would be yet another resonant frequency. This elegant idea, however, comes with a profound requirement. The mathematics of string theory only works if the universe has more than the three spatial dimensions we experience. It demands 9, 10, or even more dimensions of space. So where are they? Theorists propose they are compactified, curled up into shapes so incredibly small, on the scale of the strings themselves, that they are completely hidden from our perception. Imagine an ant walking along a tightrope. From its perspective, the world is a single, long line, a one-dimensional path. But if you were a tiny, vibrating string on that same rope, you would experience the rope's full, circular thickness. You would have access to a second, compact dimension. Our universe could be like that tightrope, with extra dimensions curled up at every single point in space. This leads to a concept of staggering immensity, the string theory landscape, because the extra dimensions can curl up in a vast number of different, stable ways. Each configuration yields a universe with different physical laws, different particle masses, and crucially, a different value for the cosmological constant, our dark energy. The number of possibilities is not just large, it is estimated to be 10 to the power of 500, a number so colossal it defies any human analogy. This landscape directly fuels the multiverse concept. Our universe, with its peculiarly small amount of dark energy, is just one accidental, habitable bubble in a frothing cosmic foam of possibilities. We do not observe a finely tuned constant. We simply inhabit one of the rare pockets where the compactification of dimensions resulted in a value that allows for galaxies and life. Within this framework, our entire cosmos might be a three-dimensional membrane or three-brane, floating within a higher dimensional bulk. All the particles and forces we know could be trapped on this brane, like waves on the surface of an ocean, while only gravity, described by the closed strings of the graviton, can leak out into the full higher dimensional space. This could explain why gravity is so phenomenally weaker than the other forces. It is not weak, it is simply diluted, its strength spread out across dimensions we cannot access. Yet for all its mathematical beauty and explanatory promise, string theory stands on shaky ground. It has yet to make a single testable prediction that can be verified in a laboratory. The energy scales required to probe the strings or uncurl the extra dimensions are far beyond the reach of any particle collider we could ever build. Some physicists see it as a magnificent piece of abstract mathematics, a potential theory of everything that remains, for now, untethered from experimental reality. Others argue it is the only game in town that consistently unites gravity and quantum mechanics, so we are left with a haunting, speculative question. Could the enigmatic presence of dark energy and dark matter be our first indirect glimpse into these hidden dimensions, a faint signal from the geometric folds of reality that are forever beyond our direct sight? The value of dark energy is not just small, it is absurdly and specifically small. If this mysterious repulsive force were even slightly stronger, the universe would have blown itself apart before stars ever had a chance to ignite. If it were slightly weaker, the cosmos would have collapsed back in on itself in a fiery crunch. The same is true for other fundamental constants, like the strength of the nuclear forces that bind atoms. Tweak them by a fraction, and carbon, the very foundation of life as we know it, would never form inside stars. This eerie precision is known as the fine-tuning problem, and it leads to one of the most debated ideas in modern science, the anthropic principle. In its simplest form, the weak anthropic principle states the obvious: we can only observe a universe that is compatible with our existence as observers. It is a selection effect, like a fish marveling that it was born in water. The strong anthropic principle, however, is far more contentious. It suggests the universe in some sense must have properties that allow life to arise. This is where the concept dovetails with the multiverse. If an infinite froth of bubble universes exists, each with different physical laws and constants, then it is no surprise we find ourselves in one of the rare habitable ones. We are not the purpose of the cosmos, but simply a possible outcome in a vast landscape of impossibility. This idea sharply divides the scientific community. For some, like Leonard Susskind, it is a powerful explanatory tool. He has argued that the anthropic principle is the only way to make sense of the vacuum catastrophe, the colossal mismatch between the predicted and observed energy of empty space. For others, it is a philosophical surrender. The physicist Paul Davies has criticized it as a conversation stopper, a lazy excuse that halts the search for a deeper, more fundamental theory. Why should we stop looking for a real explanation for the value of dark energy? He might ask, if we can simply say we live in a universe where it happens to work. This debate forces us to confront the very nature of scientific inquiry. Is our universe a unique, elegant system whose laws we can derive from first principles? Or is it one random ticket drawn from a cosmic lottery, its properties ultimately arbitrary and without deeper reason? The anthropic principle does not answer this question. Instead, it holds up a mirror, reflecting our own presence back into the equations, blurring the line between the observer and the observed, and challenging us to decide what kind of explanation we are truly seeking. The ultimate fate of the cosmos hangs on a single, enigmatic number. For trillions of years, the silent war between dark matter's pull and dark energy's push will dictate the final chapter of everything. The leading contender is the Big Freeze, a slow and lonely end. If dark energy remains a constant force, the universe's acceleration will continue steadily. One by one, the lights will go out. Galaxies will recede beyond any conceivable horizon, their light stretched into invisibility. The last stars will exhaust their fuel and fade to cold, dark embers. Black holes will slowly evaporate over unimaginable eons through Hawking radiation. Eventually, the temperature of the entire cosmos will approach absolute zero, a state of maximum entropy where no energy can be extracted, no work can be done, and no new structure can ever form. The universe becomes a vast, dark, and eternal sea of near-nothingness where even time loses its meaning. This is the heat death, the ultimate equilibrium. A more violent demise is the Big Rip. This scenario unfolds if dark energy is not constant but a dynamic force that grows stronger over time. In this future, the repulsive push would eventually overcome every force that holds things together. First, galaxy clusters would be torn asunder, their gravitational bonds snapping. Then, individual galaxies would be shredded. The Milky Way would be pulled apart. Next, the solar system would be ripped to pieces. In the final, terrifying moments, the escalating force would tear planets apart, then overcome the atomic forces holding matter together. Every molecule, every atom, every nucleus would be violently shredded in a final, instantaneous cataclysm. The very fabric of space-time would be torn apart. The once plausible Big Crunch now seems a distant possibility. This is the classic cyclical universe where the expansion eventually halts, reversed by the collective gravity of all matter. The cosmos would begin collapsing in on itself, galaxies rushing back together, temperatures and densities soaring to infinity. Everything would end in a fiery singularity, a mirror image of the Big Bang. Some theories suggest this could trigger a new Big Bang, a perpetual cycle of cosmic death and rebirth. However, our discovery of accelerating expansion has made this outcome highly unlikely, requiring a dramatic and unforeseen reversal in the nature of dark energy. Which of these fates awaits our universe depends entirely on the equation of state of dark energy, the parameter scientists call W. A value of exactly -1 points to the Big Freeze. A value more negative than -1 makes the Big Rip inevitable. Missions like the Nancy Grace Roman Space Telescope and Euclid are designed to measure this number with exquisite precision. They are not just mapping the past, they are reading our ultimate destiny. As one cosmologist reflects, we are the first generation of humans to be able to scientifically investigate the end of time itself. The data they gather will tell us whether the cosmos is destined for a quiet whisper, a violent scream, or a rebirth we cannot yet comprehend. This cosmic endgame is written in the nature of the dark energy we are now racing to understand. This grand cosmic search echoes a story as old as humanity itself. We have always looked up at the starry sky and told tales to explain its mysteries, from ancient gods and celestial chariots to our modern narrative of dark matter and dark energy. The quest to understand the cosmos is woven into our very identity. It is a fundamental human drive that transcends the abstract and delivers tangible gifts back to our small world. The relentless pursuit of these invisible forces is a powerful engine for technological progress. To catch a single WIMP, we must build detectors of impossible sensitivity, which in turn advances our mastery of ultra-pure materials and cryogenics. To process the fire hose of data from telescopes like Vera Rubin, we create brilliant new algorithms for machine learning and pattern recognition, tools that now help diagnose diseases and predict weather. This cosmic curiosity pushes the entire frontier of computing and engineering forward. It also ignites a fire in the human spirit. For every scientist spending a long, cold night at a remote observatory, there is a moment of pure wonder that makes it all worthwhile. They speak of the thrill that runs through a collaboration when a new signal appears, a collective intake of breath across continents. One researcher described the feeling of looking at a fresh dataset not as lines on a graph, but as a whisper from the universe itself, a secret waiting just for them to uncover. This endeavor is a monument to human collaboration. Teams from dozens of countries, speaking different languages and holding different beliefs, unite in a single purpose to decode reality. They share data, challenge each other's ideas, and build machines together, proving that the greatest puzzles can bring out the best in us. It brings to mind that iconic image of our world, the pale blue dot, taken from the edge of our solar system. In that photograph, Earth is a mere speck of dust suspended in a sunbeam. Every human life, every triumph and struggle happens on that tiny pixel. And from that fragile mote, we are reaching out with all our intellect and imagination to map the invisible architecture of the cosmos. So we are left with a final, humbling thought. In this grand race to decode the universe's darkest energies, are we not also, in the end, discovering something essential about the light within ourselves? The universe we call home is built upon a foundation of profound darkness. From the silent, gravitational grip of dark matter that sculpts every galaxy to the phantom pressure of dark energy, relentlessly stretching the cosmic fabric, we have journeyed across a reality where the visible is the exception. Our epic quest has revealed a cosmos where the stars and planets we hold so dear are merely the glittering surface of a deep, enigmatic ocean, a realm governed by forces we can only infer but not yet see. This grand race is a testament to our insatiable need to understand, a collaboration spanning the globe that unites the theoretical with the tangible. It unfolds in the profound silence of underground laboratories waiting for a ghostly bump, in the pristine mirrors of space telescopes mapping invisible architecture, and in the brilliant minds running simulations of cosmic dawn. We are all witnesses to a fundamental rewriting of our story, one where the answers lie not in the light but in the dark. The legendary astronomer Carl Sagan once reminded us that somewhere, something incredible is waiting to be known. That somewhere is all around us, hidden in the vast, dark spaces between the stars. So the next time you look up at the night sky, see more than just points of light. See the frontier of our greatest adventure, a mystery unfolding in real time. The race is far from over. Stay curious, follow the discoveries as they happen, and share your own wonder and questions below. Everyone has a place in this grand endeavor to pull back the veil and finally meet the dark forces that command our universe.